measurement devices to measure things. It's a flexible circuit that measures resistance, and the bridge can be balanced under certain parameters using these 4 resistors that you see. Now, we talked about sensors being plugged in over here. These sensors are devices whom will generate resistance fluctuations based on analog parameters such as light, weight, pressure, strain, heat, temperature as well, which I don't think I listed, and other analog parameters, and it's fed back in the form of a resistance. So, for example, if you were measuring temperature, you'd have a temperature sensor sticking into this location, and its resistance would change based on the temperature, let's say in the air, in the freezer, on an engine block in a car, and the resistance of that sensor would change and provide feedback to the circuit. Quite often, providing resistance changes in the 1 ohm to 1,000 ohm, 100,000 ohm range. So a very flexible circuit. What you'll notice here is that the circuit on the right is a far simpler looking circuit. Now, this is essentially a series circuit right here, and this is a series circuit. And when they're combined together, they form a series parallel circuit. So there is only one current flowing through this side of the circuit, and there's only one current flowing through that side of the circuit. Now, what we have are 2 identical circuits that with multiple values can be adjusted. And what I mean by adjusted, well, we'll talk about that in the next slide. Here's that circuit again, and up at the top is a voltage ratio. It shows that when this bridge is balanced, they insert a galvanometer here, which measures the current flow from point A to point B. And when the bridge is balanced, you are going to get in that spot a current of 0 ohms. When the bridge is balanced, there will be a current flowing from A to B or B to A of 0, not ohms, amps. Let's get that out of there. Amps. There will be a current flowing of 0 amps across that Wheatstone Bridge. Now you'll see that it's driven by a DC power supply out here in this particular chapter. We have a series circuit on both sides with one current. And when the bridge is balanced, this equation with the red star holds true. Now, why is that important? That's important because when this holds true, you will get a situation where Ohm's law, these 4 voltages are defined by Ohm's law, but because R1 and R3 have the same exact current in them, this allows you to cancel. If I could get it to sit still, let me go back here and select and lock. Select. Let me take care of a few things here. All right, let's give her a whirl, see if we can continue. If we are allowed to cancel the 2 currents on all 4 sides, because you've got a fraction with the same value on the top as the bottom, you're left with a resistance ratio to describe this circuit. You've got a voltage ratio up here that you can use. You've got a resistance ratio. And we can rearrange this formula for resistor R1, which is located up at the top here, okay? Resistor R1. Now, why we would do that is because we want to be able to balance the bridge when we use this particular circuit. It becomes important because when the bridge is balanced, no current flows, and we have essentially developed a calibration point of sorts that to solve for when the bridge will be balanced. Here's that formula down at the bottom here. Let me grab a marker. Here's that formula, and we change the values to look a little different. R1 becomes R unknown, and RV becomes R3, and we now have adjustability. We came back here and took R3 and R1. Could you use this equation here, R unknown, and use circuit? Here's where RV and R unknown are located in an actual balanced Wheatstone bridge with zero current. So R3 and R1, and we redefined what we were going to call them. We're going to call them the unknown and the variable. The variable being the sensor. Okay? So, in this chapter, all they want to teach you is how to balance the bridge. So, if that's the case, and you were given 1, 2, 3 values, R unknown is RV times R2 over R1. If you were given these 3 values, could you calculate the unknown resistor required to balance the bridge? Okay? And I think the answer is yes, you could. So in your homework problems, they're going to give you R2, they're going to give you R1, they're going to give you the RV value and ask you to balance. They might even give you a problem in the homework with a 1K, a 2K, a 3K, and a 4K and ask you if the bridge is balanced. The answer is no, the bridge is not balanced. 1/2 does not equal 3/4. So for a balanced bridge, the left and the right have to be balanced. Okay? All right. So what we said was that this here would be our sensor, and we're going to look at an example in slide 5 of a sensor that sits in here that is part of the circuit. Now, a temperature measurement, okay? So here is a temperature sensing device. I shouldn't have colored the whole thing in, but there it is. Let's put in just a circle. There's the temperature sensing device. Here is the unknown resistor. And what we do is we balance towards something we understand. For example, the thermistor, when it's put in something where the temperature is changing, its resistance is going to go up and down, okay? The resistance of the sensor goes up and down. But we do have a couple of, we have a point of freezing at 32 degrees Fahrenheit where things freeze. We could use that as a reference point, and anything at 32 degrees Fahrenheit is going to provide some sort of resistance to this component to this bridge, to this circuit. And if we balance it out by putting in a resistor here in blue, if we put a resistor in blue on that side, that balances the 4 resistors like we saw, then we have a balanced bridge. So if at 32 degrees the sensor was 1,000 ohms, okay, and we had 1,000 and 2,000 on the right, 1K over 2K is 1/2. Well, we can get 1/2 by balancing the top of the unknown resistor by 500. Did you follow that? Let's do that again. Let's say that we plug a 1K, time to rub out a little bit better. There we go. Clean that circuit up. All right. Let's say that we have a 1K and a 2K resistor. But on the bottom, we notice that at 32 degrees Fahrenheit, we get 1,000 ohms out of that sensor. And we need to calculate what the unknown resistor is. Well, I can tell you, because the numbers are nice, that 500 over 1,000 is the same as 1,000 over 2,000. Now, you're going, wow, that's cool. What if I put 2,000 over 4,000? Works. What if I put 4,000 over 8,000? Works. Balanced. What if my sensor was not at 1,000? What if it was at 4,000? Then my sensor unknown resistor would have to be 2,000 ohms. So the unknown resistor, which is located up here in red, is usually fixed. It's chosen. It's chosen to balance the bridge. You can always balance the bridge. You just have to know what you're talking about in each of the locations. For example, if you knew that your sensor had 5,000 ohms at freezing, then you could pick 5,000 for that resistor. And arbitrarily, you could pick 4,000 here and 4,000 here, and you have a balanced bridge. So, as you can see, it's not too difficult to balance the bridge. You just have to find a point of reference that you care about, so that temperature sensing resistor, that strain gauge, the pressure sensor, the weight sensor, whatever you're plugging in to this location, you have to know a little bit about that device for this to be set up. Okay, that's what's important. So the thermistor emits resistance. The bridge calibrates to 0 at 32 degrees, and then as the temperature goes up and down, what happens is the proportionality between these two change, uncalibrating the middle of this AB point, which up until then had 0 volts, which means this amplifier had no output. Now, as the left side uncalibrates, the voltage will go up or the voltage will go down, depending on which direction the resistance, which is located here, goes. If it goes up or down, it will determine whether A or B is plus to minus or plus to minus, which affects this amplifier and the voltage that it puts out. So that's getting a little more technical than we need to. And basically, you've seen this device work. It's exactly the same if you put a strain gauge out here, or you put something to measure weight, or you put a thermocouple out there, or you put a light sensing, you put a, I'm drawing blanks here, a light sensor in that position to make light sensitive decisions. For example, you've got a Malibu light system and you want to detect light and dark. And you know that at 5 o'clock in the evening it gets dark, and you want to be able to adjust whether a circuit turns on or off so your Malibu lights can start up. Or maybe you've got a jacuzzi, and you know that if the temperature is at 32 degrees and you turn it on, that it's going to start to thaw your jacuzzi and melt the ice. But at a certain temperature, you're going to want it to turn off and maintain. Well, you could use a Wheatstone Bridge in these kind of applications. I hope you found this interesting. Okay, so here's example 717 out of your book. It's just a working problem for you to see what is possible. We've taken the left side and figured out that the variable resistor is 2,500 ohms at the calibration point that we've computed, maybe for a thermistor, for example. And the other side, we've chosen 400 and 300 ohms. That's a ratio of 3/4. So if we want to match that ratio by putting 1,875 ohms up on top, 1875 over 2,500 is 300 over 400, and we have a matched bridge. Balanced, no current flow. The galvanometer that sits in the middle here in red, the galvanometer, is measuring 0 amps. Then from that calibration point, let's say we're talking temperature, if the temperature goes up or down, that galvanometer is going to show current flow.